In this short series of videos, you will learn how to calculate the crack widths in reinforced concrete structures. The series of videos are all based on the book Structural Design from First Principles, Chapter 10, Control of Cracking in Reinforced Concrete. Many elements, such as walls, are not subjected to significant loads. Instead, the main loading is from shrinkage movements which induce tensile stresses. These stresses are transferred to the steel when the concrete cracks. For example, 10.3 shows a wall cast onto a foundation. The wall is restrained from shrinkage by the foundation, which was cast first. Since shrinkage is restrained, tension cracks can form, and if uncontrolled, these can create visual defects that are particularly obvious after rain. If concrete is insufficiently reinforced, then the rebar will yield when the first crack forms, as the element shrinks due to heat of hydration movement. You can see that in figure 10.4a. Since the tensile strength of the rebar is less than the tensile strength of the slab, all subsequent shrinkage will be taken up by yielding of the rebar in the first crack formed. However, if the tensile strength of the rebar is greater than that of the concrete, then the rebar in the cracks will remain elastic. Elastic movements are much smaller than plastic ones, therefore the crack width will be less. More cracks will be formed to take up the movement, as you can see in figure 10.4b, but the crack width will be less. The guiding principle to control cracking is to ensure that the tensile strength of the rebar is not less than the tensile strength of the concrete at 3 days after casting. So, using this guiding principle, we can develop a simple relationship. The tensile strength of the concrete is simply the area of the steel in the concrete multiplied by the yield stress of the concrete, and that needs to be greater than the tensile strength of the concrete at 3 days, which is simply the area of the concrete times by the tensile strength after 3 days. So we just need to then calculate the tensile strength after 3 days. The 3-day strength of concrete is approximately equal to 1/2 of the 28-day design strength of the concrete, and the tensile strength of concrete is approximately 1/10 of the crushing strength. Therefore, the 3-day tensile strength is approximately equal to 1/20th of the 28-day design strength. The estimation of crack width is based on a very simple and empirical based method, where the crack width W is equal to the crack spacing multiplied by the restrained shrinkage strain. The restrained shrinkage strain is approximately equal to 0.75 times the free shrinkage strain multiplied by the restraint factor. The strain that would occur if there was no restraint to shrinkage is known as the free shrinkage strain. And the restraint factor is dependent on the conditions in the concrete. The 0.75 factor accounts for creep strains, which relieve heat of hydration shrinkage strains. Creep is more important for long-term drying shrinkage, where this factor can be reduced to 0.5. So the restraint factor depends on the degree of restraint to shrinkage. The worst case is when a wall or slab is cast between two rigid boundaries, and we can see that here. So we've got a rigid boundary which allows for no movement due to the tensile load developed by the concrete as it shrinks. And because there is no movement, the restraint factor is taken as 1.0. In B here we can see a plan view of a slab, and we can see some rigid boundaries around the outside. So the slab was cast first here, and then this slab was cast here, this one was cast here, and then this one was cast here. leaving these two remaining slabs to be cast last. Now, because this part of the slab provides a very good restraint to shrinkage, this will create the worst type of shrinkage cracks. So in this particular case, the restraint factor would be approximately 1.0. So that is why when we're casting slabs in bays in buildings, we don't cast them in alternative bays. So in figure 10.6 we can see a wall here that is cast onto a slab. The slab was cast first, so it has a different value of Young's modulus, because Young's modulus changes with time. As the concrete gains strength, Young's modulus increases. So when the wall is cast onto the slab, the wall will want to shrink because of drying shrinkage and also because of heat of hydration movements. And that will be restrained by a force that will be developed in the bottom half of the slab. So from equilibrium, the shrinkage force is equal to the restraint force. And the shrinkage force is equal to the area of the top half of the slab multiplied by Young's modulus for the top part of the slab multiplied by the restrained strain, which is epsilon r. And that will be equal to the restraint force, which is the area of the bottom half of the slab, multiplied by E for the bottom half, and now by the movement of the bottom half, which will be the free shrinkage strain minus the restrained shrinkage strain. So dividing through by epsilon free, we have this expression. So the restrained shrinkage strain in the concrete is equal to the restraint factor times the free shrinkage strain. So we can, with that, calculate the restraint factor, R, and the crack spacing is defined using a Eurocode 2 expression, which is given by 3.4 times the cover plus 0.34 times the rebar diameter divided by the reinforcement ratio. I hope you enjoyed this short video on the control of cracking in reinforced concrete. There are 6 more videos on this topic available on YouTube and also in the book Structural Design from First Principles. I hope you enjoyed this, and do press like if you found it useful. Thank you.